Hello everyone, today I'll talk about the solution to the problem find kth bit in nth binary string. Problems like this have multiple approaches that you can try. In particular, I think in this problem it would work to just generate the nth binary string by the rules that were given here and return its kth bit. I think that would work, but of course that's not the best solution. And while there is probably something that can really get deep into the structure of the string in order to quickly and easily answer what the kth bit of the nth string is, I think the best balance between having to think deeply about the structure and actually having a fast solution is an approach that looks at the fact that the string is generated in a recursive fashion and tries to calculate the corresponding bit in the nth string in the same recursive fashion. So we try to re-implement the rules for string creation, and by re-implementing them we can, well, access the bit that we're interested in. And for instance, when it comes to calculating that bit in this case, we know that if we know the length of the ith string, then the bit is either exactly in the middle, in which case we know that the bit is equal to 1, or it is in the first half, in which case we can recursively just calculate that same bit in the previous string, or it's in the second half. So the second half is the reverse of binary flipping of the previous string. So our position is the same but from the other side, so we have to take our position, subtract the length that's before the position in the ith string to get the position in the I minus first string, and then calculate that position not from the left but from the right. And since we also have this invert operation, we have to negate the result, flip the result. But in other words, we can essentially again recurse on the previous string and do something, change that bit appropriately and return the result. And this is the approach that doesn't require essentially thinking about any mathematics, just implementing what we have here, and it's fast. And in problems like this where we have essentially exponential growth in the length of the string, it's logarithmic with respect to the length of the string, or it's simply linear with respect to n in this case. So we know that we have to be able to decide if we're in the middle, in the first half of, or in the second half. So we have to be able to tell what length is the string that we're currently looking at. Now, if you know something about recursion, you might know that starting with the length of 1, and each next string being twice the length of the previous one plus 1, then this will be a sequence of powers of 2 minus 1. This is pretty interesting, so you can see it for yourself, but you don't have to do it, you don't have to know it to solve this problem, because you can just calculate the lengths of all the strings before, as a pre-processing. So the first string has length 1, and each next string has length twice the previous length plus 1. So if you want, you might just print those sizes and you will see that those sizes are 1, 3, 7 and so on. And you might try to prove it if you like a little bit of easy mathematical exercises. Anyway, in the sizes list we have pre-calculated the lengths of every string in the sequence up to the nth string which interests us. And we'll have a function that will be recursive to calculate the appropriate value for the bit. By the way, I'm going to add, in a way different from this task, start numbering from 0. I think it's more natural in this case. So we'll be asking for at the beginning, the k minus first bit of the n minus first string. And this will just return true or false, depending on if that bit is 1 or 0. So at the end we can just return it. And now, of course, all that's left is the specifics for how to recurse and what is the base case. The base case is, of course, if we have the 0th string, so the string consisting only of a 0, we return that 0. Otherwise, we know that the size of our current string is sizes of n, which is pre-calculated here. So the index of this middle one is exactly size divided by 2 rounded down. And now if we're asking for exactly this one, we return this one. Otherwise, if we're asking for something to the left of this one, so k is smaller than mid, we return the kth bit of the previous string, of the n minus first string. So that is all that we have to do. Otherwise, k is to the right of our size. So we have to go again to the previous string. And now the position is, first of all, we have to subtract mid from k in order to get the position in the second part. In fact, the position in the second part at first is k minus mid minus 1. And we also have to count it not from the left but from the right. So instead of the ith position, we would get the size minus I minus first position. So essentially here we have minus 1, and here we have sizes minus position minus 1, so the two minus 1s cancel. Anyway, if it's not very clear to you, then just try to imagine if you have a string and you have position I, then what is the corresponding position from the back of the string? And you would arrive at exactly this kind of situation. And so this is essentially the re-implementation of the rules that were given, and they allow us to calculate the bit in time proportional to n, so very quickly in this case.